Welcome to the second session of Let's Learn RAG. In the previous session, we explored the overall RAG architecture and took a deep dive into embedding models, what they are, how they work, and why they are so powerful. In today's session, we are going one level deeper. We will focus on two key components that make retrieval truly intelligent: vector databases and similarity search. We will not only understand the key concepts, but also walk through real examples and code. So, without wasting any more time, let's dive straight into vector databases, a core building block of modern RAG system. So, what exactly is a vector database? A vector database is a specialized database designed to store, manage, and search high dimensional vectors, also known as embeddings. These vectors are numerical representation of complex data like text, images, or audio, capturing their semantic meaning in a form machine can understand and compare. But why do we need a vector database in the first place? When we convert something like a sentence into numbers using embedding model, we don't just get a few values. We get a high dimensional vector, often with 384, 512, or even 768 numbers. These vectors aren't just a random, they capture meaning and semantic content of the input. So now the challenge is, how do we store these large vectors efficiently? And more importantly, how do we search and compare them quickly to find similar meaning content? That's exactly where vector databases come in. Traditional databases are great at searching for exact matches or using basic filters like keywords, IDs, or categories. But let's say you ask, show me all documents related to quantum algorithms. A traditional database might miss relevant content if it doesn't contain those exact words. This is where vector representation become powerful. Embeddings capture the meaning of the text, not just the words, and allow us to compare content mathematically using similarity metrics like cosine similarity. So now, even if your query uses different words, the system can still find semantically similar documents, making search much smarter and more human like. Now let's understand how vector database actually works. It's designed to handle three main tasks: store the vectors, index them efficiently, search through them quickly. Let's go through each step one by one, starting with the first: store. When we receive unstructured data like a sentence or paragraph, we first pass it through embedding model, which converts it into high dimensional vector. This vector then stored in the vector database along with the optional metadata like original text or document ID. Now that we have stored our vectors, the next challenge is, how do we make searching among millions of vectors fast and efficient? This brings us to the second core part of vector database: indexing. When vectors are added to the database, it automatically builds an index to organize them. Just like how library catalog helps you find a book faster. This indexing is critical, especially when you are dealing with millions of vectors. It's what makes similarity search fast and scalable. There are several popular indexing techniques used in vector databases, first one being HNSW, which is Hierarchical Navigable Small World. This is known for being both fast and accurate. Then there is IVF, Inverted File Index, which is commonly used in files. Other options include Annoy, Scann, etc. Among these, HNSW is one of the most widely used and powers many modern vector DBs like Chroma and queried. So next, let's do quick deep dive into HNSW just to understand how indexing works behind the scenes and how it helps retrieve information faster without scanning the entire database. HNSW stands for Hierarchical Navigable Small World. It's a graph based algorithm used by vector databases to perform fast and approximate nearest neighbor search. Now imagine you have millions of documents all converted into vectors. You want to find the ones most similar to your query. Instead of comparing your query with every vector, which would be slow, HNSW navigates a graph of vectors, hopping between nearby points to quickly zero in on the closest matches. So, how does it work? HNSW builds a multi-layer graph structure of all the vectors. Each node is a vector connected to its nearest neighbor. The graph is built in layers. Top layer has very few nodes, gives broad, zoomed out overview. Middle layers contain more nodes and offer moderate level of detail. Bottom layer includes all the vectors, providing fine-grained connections. You can think of this structure like a pyramid. The top layer has very few nodes. As we move down to the middle layers, there are more nodes offering a more detailed view of the space. Finally, at the bottom layer, we have all the vectors. The search starts from the top layer and moves downwards, getting more accurate at each level, kind of like zooming into a Google Maps from a world view down to the street level. This makes HNSW both fast and precise, which is why it's a backbone of many production grade vector databases. Let's understand indexing with a simple example. Imagine we have a small document store with the following 5 sentences, each covered into a vector using an embedding model. We have also grouped them based on their semantic meanings. You can see that sentences A, B, and C are semantically similar. They belong to the healthcare group. Similarly, D and E are part of quantum group. Even though actual words are different, the embedding vectors for each sentence are close in vector space because their meaning are similar. When indexing is applied, the vector database will naturally place the similar vectors close together so that retrieval later is fast and accurate. Now let's see how these 5 vectors are actually organized in HNSW's layered graph structure. We will keep it simple with just 2 layers, where layer 0, the bottom layer, this is most detailed layer. It contains all 5 vectors connected based on semantic similarity. For the healthcare group, A is connected with B and B is connected with C. These are closely connected because of similar meaning. And for the quantum group, B is connected with E. These are like local neighborhoods in the graph where nearby points are connected. On the other hand, layer 1, the top layer, this layer is sparse and meant for fast travelers. One representative of each group. A for the healthcare cluster with pointer to B, and D for the quantum cluster with pointer to E. Now, let's move on to how search happens step by step. Let's assume the user inputs a query called quantum entanglement research. As a first step, we convert the query into vector embedding. Then, the search starts at layer 1, comparing similarity with A and D. Since the query is all about quantum, it is more similar to D. So we move to layer 0 starting from D and exploring connected nodes like E. Based on cosine similarity scores, we return the top k most similar vectors, which in this case would be E and D. Now, this flowchart summarizes that entire process visually step by step to make it easier to understand. We begin at layer 1, where the query vector is compared to key entry points, in this case, node A and D. Since the query is related to quantum, the system identifies D as more similar and moves down to the quantum cluster. At layer 0, the graph continues traversal, now comparing with node E, which is directly connected to D. Finally, the system returns topmost similar vectors, in this example, D and E. This shows how HNSW graph allows system to skip irrelevant parts of the databases and quickly find the most meaningful matches layer by layer. Now that we understand how indexing works behind the scenes, let's move on to the final piece of vector database, the search process itself. The search flow is actually quite straightforward. First, we take input sentence, in our case, our query, and pass it through embedding model to get vector representation of that query. Then the query vector is compared with all the vectors stored in the database, in this case, our 5 example sentences. Then the system returns top k most similar vectors based on similarity score. The value of k is hyperparameter here, meaning we can configure it based on how many results we want to retrieve. For example, top 3 or top 5. So we are not just retrieving random documents, we are retrieving the ones that are mathematically most similar in meaning to the input query. Now, this brings us to a very important question. How does the system actually measure similarity between vectors? That's where similarity search comes in. So, what is similarity search? It is the process of finding items like texts, documents, or images that are most similar in the meaning to a given input. And this is the key difference. Instead of matching exact words, we are comparing semantic meaning using vectors. This is what makes vector database so powerful. They allow us retrieve information intelligently even if wording completely different from the query. So whether you search for a schedule a doctor visit or set up a medical consultation, the system knows they mean same thanks to similarity search. But how exactly does the system measure similarity between vectors? That's where concept called cosine similarity comes into play. Instead of comparing the distance between vectors, it compares the angle, helping us understand how aligned two meanings are in the vector space. Let's break that down next. To build a better intuition for cosine similarity, imagine each vector as an arrow pointing in a certain direction in space. Now, what we care about is the angle between these two arrows, not how long they are or how far apart they are. If two vectors point in the same direction, the angle between them is 0 and the cosine value is 1, meaning they are very similar in meaning. If they point completely different direction, say 90-degree apart, the cosine value drops to 0, which means they are unrelated. In rare cases, if vector points in opposite direction, cosine becomes -1, which means they are as opposite as possible, though this rarely happens with sentence embeddings. So cosine similarity gives us normalized measure of how closely two meanings align, regardless of their length or scale. And that's exactly what we need for semantic search. Let's now walk through a simple example to see cosine similarity in action. We will take three sentence embeddings. Let's pretend we got this from an embedding model. Before we jump into the example, let's quickly look at the formula for cosine similarity and understand what it means. Here is what each part represents. A dot B is the dot product of the two vectors. It tells us how much the vectors are pointing in the same direction. Pipe A and pipe B are the magnitudes of the vectors, calculated using the square root of the sum of squares. So the cosine similarity compares the angle between two vectors. Let's compare the query with S1 using cosine similarity formula. Let A be the query and B be the S1. After inputting all the values, we get cosine similarity as 1. This means query and S1 are very similar. Similarly, if we calculate cosine similarity scores for all the sentences, we get something like this. We see that S1 and S2 are very similar to our query. On other hand, S3 is completely different. This shows how cosine similarity allows us to mathematically compare meaning, not words, and retrieve the most relevant content based on direction and not distance. Let's quickly summarize what we have learned so far. Vector databases stores documents as a vector, also called embeddings, built especially for fast and efficient similarity search. On the other hand, similarity search finds the top k most relevant chunks to your query. It uses cosine similarity to compare semantic meaning, not just keywords. So, final takeaway is when you combine vector databases with similarity search, you give machine the ability to retrieve information the way humans think, by meaning and not just word. Now that we have a strong, in depth understanding of how vector databases and similarity search work, let's move on to the exciting part, implementation. We will now see how to put all this into action by using Chroma DB to build similarity search system on top of quantum computing nodes dataset. This will help us connect theory with practice and understand how everything comes together in real RAG workflow. Before we jump into implementation, let's first take a quick look at the quantum computing nodes we will be using to build our knowledge base. This document contains structured lecture material on quantum computing, but like many PDFs, it includes some pages that aren't useful for our system. So as a first step, we will remove first 9 pages which include index, cover and a few blanks. Once we clean that up, the revised version of notes will look like this, with content starting directly from chapter 1, quantum computing. This cleaned up content will be foundation of our knowledge base which we will embed, store and search using vector techniques. Now that we have seen the cleaned up quantum computing nodes, let's move on to the pre-processing step where we convert PDF into .txt file for easier handling. As a first step, we will import few essential libraries. Then we use simple helper function that reads PDF page by page and extract the raw text content. Once extracted, we will save the entire cleaned content into file called qcnotesrevised.txt. This txt file will make it much easier to handle downstream processes like chunking, embedding, and storing into our vector database. Now that we have saved our clean.txt file, let's walk through the code implementation steps, turning this raw text into a searchable vector database using Chroma DB. As first step, we will use well-performing sentence embedding model that's great for semantic understanding in English. Next, we read our QC revised.txt file. This contains all the clean content from the QC notes. Since transformer model have context limit, we need to break the long document into smaller chunks. Here, we use chunk size of 500 characters with an overlap of 100 characters. The overlap is very crucial. It ensures we don't lose context at the boundaries of each chunk. For example, a paragraph that splits between two chunks will still have enough continuity. This step sends each chunk through the embedding model, converts it into a vector, and stores it in a local Chroma DB database under the QC docs collection. The persist directory saves the database locally so it can be reused without reprocessing everything from scratch. At this point, we now have a fully functional knowledge base. Our quantum nodes have been vectorized, indexed, and stored. All that's left is to test it by running a query. As a final step, using Chroma DB, we now perform a similarity search. This line takes a natural language query, converts it into a vector, and returns the top three most semantically similar chunks from the quantum nodes. Let's now look at a real output from our retriever pipeline just to see how everything we have built actually works in practice. For an input query, what are three reasons to study quantum computers? Our system processed the prompt, embedded it, and searched the quantum nodes stored in our Chroma DB vector store. Here is the top matching result written from the knowledge base. As we can see, the retrieved chunk directly addresses the user's question and gives three detailed reasons here. Here are three reasons to study quantum computers from the practical to more philosophical. This result is highly relevant and was retrieved purely based on the meaning, not keywords. thanks to our embedding model and cosine similarity search using Chroma DB. So now we have a working retrieval pipeline that can pull out the most meaningful chunks from our knowledge base. In the next phase, we will go one step further by feeding this retrieved context into a language model and generating a complete answer in natural language. In the next video, we will cover prompt templates and explore how to integrate with an LLM for response generation. Let's move on to the generator phase of our RAG system. So stay tuned and see you in the next video.